All right, now a little bit more to finish up Chapter 2. The last part of our learning objective suggests that we need to be paying attention to how, given a set of atoms, one can determine which atom is going to have the largest radius. This follows from other things we have learned about the structure of atoms. So let's see how that works. If you look at this information from your textbook with some nice diagrams and actual values, we can see the the distance between nuclei for different elements. The one on the left would be chlorine molecules, Cl2. The one in the middle is carbon. And for the one on the right, you have chlorine and carbon. The distance between the nuclei is going to be dependent on the size of the particular atoms, the atomic radii. And so if you figure out that two chlorines together have a distance of 198 picometers, which is, by the way, picometers is 198 times 10 to the minus 12 is picometers. That's pretty small, right? We're talking atomic dimensions here. Then the radius is going to be half of that. In other words, half of 198 would be 98 picometers. The diameter, the distance between the two carbon atoms being 154 picometers. Well, if you want to know essentially the approximate radius for the carbon atom, it should be half of that. So split that by 2, and you should get 77 picometers. So carbon atoms appear smaller than chlorine. And if you put them together into the same compound or a bond to one to the other, chlorine with carbon, you would predict that the distance between the nuclei should be essentially the sum of the distances of the radii combined. And so you predict 99 plus 77, which gives you 176 picometers, and the actual measured distance is 178. Comes out pretty close. It's a reasonable way of approximating these things. So we can use atomic radii to get a perspective on the sizes of molecules and things like that. So how do those patterns work? Well, chlorine and carbon are different sizes, but why? Well, it has to do with all these things we've learned about electrons and protons, etc. So next picture. This chart gives us a generalization that works quite nicely to show you where the largest and the smallest atoms on the periodic table are. So the radius is going to increase, if you look at the left side of the chart, as you progress down a column in the periodic table. Well, this makes sense because here you have only one shell, and here you have two shells, and each shell is successively larger and a greater distance from the nucleus. So it makes sense that larger is going to result as you add shells to the atom. However, we have to figure out what makes things smaller. So the things that contribute to making an atom smaller have to do with what's in the nucleus, the electrons that are in these different shells. So if you look at, for example, the second shell, the noble gases aren't included here, so we won't have that. We can't talk about the first shell. But if you look at the second shell, starting with lithium and progressing across to fluorine, you get progressively smaller and smaller, down to fluorine being the smallest radius for that row. Well, why is that? All their electrons are going to be different by each element, but it's going to be a combined effect of the electrons and the nucleus. So for the second shell, let's start with lithium. Lithium has 3 protons and 3 neutrons in the nucleus. And then it's going to have an electron here, going to have 1 electron and another electron in the first shell. And then the second shell is going to have 1 more electron for a total of 3 electrons. Compare that to fluorine. Well, fluorine similarly has 2 shells because it's a second row element, second period element. And I'm going to draw my diagram carefully here. Fluorine would have 9 protons, and well, let's see, the atomic mass of fluorine suggests that probably there might be 10 neutrons, but that's okay. They don't have a charge. They're part of the nucleus. And so the electrons for fluorine are going to have 2 in the first shell somewhere. And then the remaining electrons, they're going to be 1s2, then 2s2, 2p5. So there's 7 electrons out here, if you can count that high, in the second shell. And I'm not showing you s and p orbitals at the moment, but let's just think in terms of how far away from the nucleus that second shell is and what it contains just in a general sense. So 1, 2, 3, 4, 5, 6, well, let's put in one more. 7 electrons in that shell. So if you think about it, the second shell is a similar distance from the nucleus for either one, but in initial concept. But if you have 9 electrons in the fluorine atom pulling against all those electrons at that distance, the pull of the 9 protons is going to be a lot greater than 3 protons on electrons at that second shell distance. So there's a big difference in how the overall effect is in the radius of the atom. So lithium will have a larger atom, larger radius, than fluorine will. The same property applies across other rows, so the radius decreases going to the right. There's another way of explaining this in terms of charges. So lithium, the fluorine 9 protons pull on 7 electrons is greater than the 3 protons pull on 1 electron in the second shell. Greater because the ratio of the pull, the magnitude of the charge is really large. Okay, so there is a chart that we looked at the very beginning of the chapter that helps us to generalize this pattern again, and let's make sure it makes sense to us because it's essentially what was shown on the previous diagram. For the patterns in atomic radii, we noted before that the maxima are going to be largest for its group 1a elements, and then the minima were going to be in the halogens, the group 7a elements. And notice that if you look at this pattern, the radius goes down across a period quite consistently. And that is exactly what we showed on the previous slide, but it has to do with those protons and electrons and how they're pulled from a certain distance by how many protons. So if you go down a column, you'll get larger value, and as the column, going down the column, the radius increases. And if you go across the row, left to right from this context, then the radius will decrease. All right, that's consistent with what we saw on the previous slide, so let's go back to it. Remember where the largest ones are. Largest here, and the smallest ones are going to be up here instead, small. A nice generalization that helps us. Okay, so what's the deal? I was just trying to explain to you how the electrons in the second shell of fluorine are pulled by 9 protons versus electrons in the second shell of lithium being only pulled by 3 protons. And this has to do with what we call effective charge, effective nuclear charge. The effective nuclear charge tells us how much charge is perceived or effectively occurring on an electron in a particular shell. So the effective nuclear charge is expresses how the valence shell electrons are attracted to a nucleus. And so what effect that has on the atomic radius is shown in this chart. So if you think about sodium right here, it's going to apparently have a low effective nuclear charge because it has 11 protons and it only has 1 valence shell electron. And so that 11, the outer shell electron, is shielded by the 10 inner shell electrons. So the effective charge is going to be the total nuclear charge, in other words, the atomic number, minus the inner electrons, the non-valence electrons. And so for sodium, that is going to be 11 minus 10 inner electrons, all but the outer one, is going to be 1 effectively. And if you compare that to something else like, let's do chlorine. Chlorine here, you're going to have the effective nuclear charge is going to be the nuclear number of protons minus the number of inner electrons. And so the number of protons in chlorine is 17. The inner electrons is 10. And so the result is the effective nuclear charge is more like 7 instead of the number that instead of 17. So you have the effective nuclear charge much greater for chlorine, and so it's electrons in that third shell this time. The sodium and argon are both in the third shell, have a greater attraction, a much greater nuclear charge than the sodium, and this isn't quite showing accurately in this graph, but that means that the charge is pulling very strongly against the valence electrons, and so as this effective charge increases, the valence shell electrons are attracted strongly, and the radius will decrease, giving us the pattern that we've seen in the last couple diagrams. So sodium has a much greater radius than argon for all of these being third period elements. Third period. Krypton is not, argon is included in this case. Wrong one. Argon is in third period. All right, so let's talk about this in terms of one more example. See if we can figure out what we're doing. Okay, so if you could see atoms represented as spheres, and they're given values for their radii in different numbers of picometers, that's the range of size for atoms, which one would be corresponding to these different atoms? Now, you wouldn't know without someone telling you how many picometers to expect for anything, so don't expect that. But we have values provided, and now we need to decide, based on our prior information in this prior conversation, which ones are likely to be the smallest and largest, and which would be in between. Okay, so think back to our periodic table. The periodic table has the largest radii are in the lower left corner, and the smallest are in this upper right quadrant, upper right corner. And we need to decide where calcium, strontium, and bromine lie in this particular scheme. So in a general sense, calcium here, strontium is below it. So calcium should be smaller than strontium. And then the bromine is in the same row as calcium, way over on the other end of the row. Which period is that? That would be the fourth period. And so of the bromine, so calcium should be smaller than strontium because it has one fewer outer shell. And bromine is in the same row as calcium, the same number, it's the outer shell electrons, or the valence electrons, are fourth period. And so which one is going to be smaller of those two? Calcium should be also smaller than bromine. Now, we have to think about it just a little bit further. This does require some thinking. You can't automatically know these things altogether, so it helps to think them through some more. So when we know that calcium is going to be smaller than, whoops, I said that backwards. Calcium is going to be larger than bromine. We want the smaller end of that row is going to be bromine, and then the calcium will be smaller than strontium. So the difference between calcium and strontium is hard for us to predict, but they're going to certainly be larger because they're on the left side of the periodic table. So the smallest one should be bromine, and then we have to decide between the other two which one should be calcium or strontium. Well, look what, the difference isn't huge, but the one that's smaller better be calcium, and the larger one better be strontium, because it's going to be one more shell larger, but it's surprisingly not huge in the difference in the radii. And if you go back and check into our prior diagrams, sure enough, there it is. Calcium and strontium have correspondingly the values we just observed, and bromine is very tiny by comparison. So it's interesting how much difference that effective nuclear charge for bromine is going to make. Remember, 35 is the atomic number of bromine, and the inner electrons are going to be somewhat shielded, but that leaves still quite a greater effective nuclear charge to pull on the outer core electrons. All right.